Hi, and welcome to 4.6 Newton's Third Law. Newton's third law states that for every action, there is an equal and opposite reaction. So for every force, there's an equal and opposite force. This worksheet was put together with questions from the physics classroom. Thephysicsclassroom.com is a great website. If you need some extra help with physics, it explains all the concepts, and it's very organized. I like that website a lot. I also put some questions for the regents here. So this is a pretty decent worksheet for Newton's third law. So for number one, for each stated action force, identify the reaction force. The bat hits the ball, and it causes the ball to go forward. The ball hits the bat, and you feel the resistance. If you ever hit a ball before with a baseball bat, you could feel that shock in your hands. So, that's just that simple. The ball hits the bat. If a man pushes on the car, certainly not an easy task. You could feel the car pushing back on you. There's some resistance there. The car pushes on the man. If a bus hits the bug hits the bus. Bug hits the bus. So if you really think about these questions, especially this bug hitting the bus, they're equal and opposite forces, but they're also separate objects. So each object gets its own free body diagram, and each object might react differently to these equal forces. So for example, the bus is supermassive. The bug is exerting a force on the bus, but obviously it's not enough force to do any kind of noticeable acceleration or damage on the bus. That bus exerts an equal and opposite force on the bug, and the bug dies. It's enough force to kill the bug. The bug isn't as massive as the bus is, so it gets affected differently by this equal force. The force is equal, but the effect may be different depending on what the object is, how much mass it has, etc. For number two, describe the action-reaction force pairs in each of the following diagrams. I'm not going to write it out. You could write it out in your own words, but I'll just talk about it. The athlete pushes on the ball pushes back on the athlete. The foot pushes on the floor pushes on the foot kicks the ball exerts a force on the foot. It looks like the toe is getting hurt because it has not a good form there. Okay. All right, so number three, true or false? As you sit in your seat in the physics classroom, the earth pulls down on your body with a gravitational force. The reaction force is the chair pushing upwards on your body with an equal magnitude. If false, correct the answer. This might seem a little bit weird because the inanimate object, the chair, is pushing on me? Yes, this is true. If this is you and Earth is exerting a force downward on you, and you're sitting in the chair has to be exerting an equal and opposite force up. This normal force, which we'll talk about in the next lesson, that's the force that's balancing you out. Because if there were no normal force, if the chair weren't pushing up on you, then look, if this is the only force, you would be accelerating downward. The net force would be down. So there must be a force that the chair is exerting, the normal force, right here. So that's true. Shirley Board sits in her seat in the English classroom, because it's English, so Shirley, she's bored. The earth pulls down on Shirley's body with a gravitational force of 600 newtons. So we could draw a free body diagram. Fg equals 600 newtons. Describe the reaction force of the force of gravity acting upon Shirley. Surely it must be 600 newtons in the opposite direction. Equal in magnitude, opposite direction. Again, we could call this the normal force if we'd like. You could, if you want to describe it, you say equal in magnitude, opposite in direction. Okay, so these ones are a little strange. Number 5, okay, it says use Newton's third law, law of action-reaction, and Newton's second law, law of acceleration, A equals the F net over m, to complete the following statements by filling in the blanks. So for A, it says a bullet is loaded in a rifle and the trigger is pulled. The force experienced by the bullet is blank the force experienced by the rifle. I would say equal to. Equal to. The resulting acceleration of the bullet is blank the resulting acceleration of the rifle. If you've ever shot a rifle before, you can feel the kickback. So the rifle is definitely accelerating here. But is it accelerating as much as the bullet? Well, if we look at the law, it's Newton's second law, we could set up a fraction, and we're going to do one for the bullet and one for the rifle. Okay. So, the forces for each are going to be equal. But the rifle is a lot more massive than this bullet. And if you know anything about fractions, the greater the number in the denominator, the smaller the acceleration is going to be. If it's a small number in the denominator, the acceleration will become greater. So the bullet accelerates more than the rifle does, even though the forces are equal, because they have different masses. Kind of cool. So the resulting acceleration of the bullet is going to be greater than the resulting acceleration of the rifle. A bug crashes into a high-speed bus. The force experienced by the bug is going to be equal to. It's equal to the force experienced by the bus. The resulting acceleration of the bug is blank the resulting acceleration of the bus. Just think about it. Which one would accelerate more? Is the bug going to accelerate more? Or is the bus going to accelerate from this crazy big... Is it a crazy big bug crashing into the bus, causing it to accelerate? No, the bus doesn't really accelerate that much at all. It's negligible compared to the bug. You could look at our fractions up above here. The rifle is now the bus, and the bullet is now the bug. The bus is more massive, so it doesn't accelerate as much. The acceleration of the bug is greater than. Again, greater than. A massive linebacker collides with a smaller halfback at midfield. The force experienced by the linebacker is going to be equal to the force experienced by the halfback. The resulting acceleration of the linebacker is blank the resulting acceleration of the halfback. The question says the linebacker is more massive than this smaller halfback. So the linebacker is going to accelerate less than the halfback because he's more massive. So the thing that has more mass has less acceleration. The thing that has less mass has more acceleration. Okay, so letter D said 10 ball collides with a 14 ball on the billiards table. Assume equal mass balls. Interesting. They're balls of equal mass, so it's not this bullet rifle situation where we have different masses. Okay, so the force experienced by the 10 ball is going to be equal to. The force is always equal to when you're talking about action-reaction pairs. The force experienced by the 14 ball. But since they're equal in mass, the resulting acceleration, what do you think? Must be equal to the resulting acceleration of the ball as well. Because, again, we could do the same thing. We could do 10 ball, and we could do the 14 ball. Okay, Same force over, they're equal in mass. So that will give you an equal, it's like a ratio to find this acceleration. Newton's second law, very good. All right, so the physics regions problems here. Shows you a diagram of a compressed spring between two carts initially at rest on a horizontal frictionless surface. Cart A has a mass of 2 kilograms. Cart B has a mass of 1 kilogram. A string holds the carts together. The string is cut and the carts move apart. Compared to the magnitude and the force, compared to the magnitude of the force the spring exerts on cart A, the magnitude of the force the spring exerts on cart B is the same. Equal and opposite forces. Now, if it asked about the acceleration, that would be an interesting question. Why don't you answer in the comments below? Which cart has a greater acceleration and why? Does cart A have a greater acceleration or does cart B have a greater acceleration? Comment below. Comment below. All right. Number 7. A carpenter hits a nail with a hammer compared to the magnitude of the force the hammer exerts on the nail. The magnitude of the force the nail exerts on the hammer during contact is the same. So these are all, they're kind of similarly worded. It's like compared to this. If they're doing that, more often than not, these questions are gimmies. It's going to be the same force. 8. Earth's mass is approximately 81 times the mass of the moon. If the Earth exerts a gravitational force of magnitude F on the moon, the magnitude of the gravitational force of the moon on Earth is still F, believe it or not. Same force, equal and opposite action-reaction pair. Even though one is more massive than the other. And we'll talk about that more. It's not a law of motion, but Newton has another law, the universal law of gravitation. That says that Fg is equal to G, m1, m2 over r squared. So the force that you calculate, it takes into account the mass of both objects. So it's an equal force. You could calculate it for one and then the other, but you'd be doing the same calculation both times. You get the same force when you do that calculation. That's in the next unit or two. Number 9. A person weighing 785 newtons on the surface of Earth would weigh 298 newtons on the surface of Mars. Interesting. What is the magnitude of the gravitational field strength on the surface of Mars? Whoa, this is great. What? This is not action-reaction pair. Totally different question. This is like a question from the previous homework, 4.5, mass and weight. So the best thing to do here is write out your given information. So the Fg for Earth, your weight is 785 newtons. You know the gravitational field strength on Earth is negative 9.8 newtons per kilogram. If you wanted to think of it as acceleration due to gravity, it's negative 9.8 meters per second squared. And that's all they tell you. And then they say, on Mars, your weight would be 298 newtons. And again, technically, these forces are going downward, so you would make them negative. And that's all. Then it asks, what is the gravitational field strength on Mars? Two different ways you could go about it. For me, I would calculate the mass. What is the mass of this person? And then once you know what the mass is, you can use that to find the gravitational field strength on Mars. So let's find the mass, because the mass is not going to change. So I would do for Earth, I would do Fg equals mg. So negative 785 is equal to the mass times negative 9.8. So the mass of this person is equal to around 80.1 kilograms. 80.1 kilograms. they don't lose an arm or anything when they go to Mars. The number of atoms roughly stays the same. So you could say that they're still the same mass, 80.1 kilograms, when they're on Mars. So, this is now for Mars. What is the gravitational field strength? Fg is equal to mg. Their new weight is negative 298 newtons. Their mass, we calculated, is 80.1 kilograms. And we're looking for g, little g, the gravitational field strength on Mars, which is about 3.72 newtons per kilogram, which is choice C. All right, so that was like more math than the other one. The other way you could do this is just kind of set up a proportion, but I like doing the math way. Math is fun. In case anybody's still not sure about this gravitational field strength idea, it's basically it's just measuring the strength of the gravitational fields. If I have Earth here and I have some mass here, okay? Let's say it's 1 kilogram of mass. Well, how much force would that kilogram of mass feel? The gravitational field strength tells us that it's 9.8 newtons for every kilogram of mass that you place at this point. So now we don't have to theoretically put a mass at this position. We know that at this position in the gravitational field, you would have 9.8 newtons for every kilogram of mass that you have. So if you have 2 kilograms of mass there, it would be 9.8 times 2. You'd have 19.6 newtons of force. If you had 5 kilograms at that position, you would have 49 newtons of force. It's just a way to measure how strong the field is. And as we saw from the number 9 here, Mars has a weaker gravitational field. So the gravitational field strength of Mars, for that 1 kilogram, you would have only 3.72 newtons of force. 3.72 newtons per kilogram. So what would that be? 7.4. If you had 2 kilograms at this position, you'd have 3.72 times 2. So 6.74 or 7.4. I can't do mental math right now. Okay. Anyway, I don't know if that helped or hurt with the gravitational field strength idea, but as we do more problems, hopefully you'll think more about it and kind of solidify what that is. All right. Have a good day. Bye.